Hello, Dr. Razouk. This is our EC-174 final project. My group consists of me, Hayssam Stokes, Adam Garabedian, and Yue Yang. Go to the next slide. So our project objectives are the following: was to overarchingly design and verify a 32-bit 5-stage pipeline MIPS processor. We broke it down into 5 stages. Stage 1 being specification of architecture, stage 2 being the RTL hardware prototype, stage 3 be the model simulation and verification, stage 4 code analysis, and stage 5 actually implementing it on an FPGA.
So here is our architecture. First, we have 16 different instructions. We support a multiplier and divider also. And then we have our 5-stage pipeline data path with control units. And on the left side is the fetch and the decoding execution mem stage and the readback stage. We also support the external input to the instruction memory and as well as the data memory at any specific address. And also we have the PC reset here. So we have the hazard detection and for the stall and the branch detection for the control hazard, and the forwarding unit is for the data hazard.
Okay, so first unit we're going to take a closer look at is the register file. So a register file is 32 registers. Each one is a width of 32 bits. And at least for the sake of this project, none of them have their special functions except for the 0 register, but everything else pretty much acts like an S or a T register. So to have this fit into the pipeline correctly, originally with the first ICA, or the ICA that we did on this, it was a combinational input and then sequential output. But now we have it read on the rising edge. Sorry, we have it read. It gets written to, which would be the register file reading on the negative edge of the clock, and then it would push out the data on the positive edge of the clock to the register file. And so you can see in the bottom right a test of the register file, and also in the middle right you can see that we have a just an output, a scripted output of how our registers read.
So the next major component of this project is the ALU. The point of the ALU is just to do the actual computation for the device, so it needs to be able to support all the instructions that can be seen on the right, except for some portions are dealt with outside the ALU, but all go through it at some point. So ALU actually consists of 2 parts: the ALU, the computational portion, and then the ALU control, which is a local controller that takes in the functions from the binary instruction and the ALU opcode that comes from the main controller of the system. And from there, it decodes the ALU control to actually select the instruction output that the device desires. As we look on the bottom left is just the ALU running with various instructions, ALU opcodes, and functions. And as we can see, we can track the result and whether it's 0 as well. That's pretty much it for the ALU. Moving on to one of the subcomponents inside the ALU is the multiplier and divider component. So part of the specifications was a serial divider and multiplier, and specifically the optimized version of it. The optimized version is able to reuse pretty much all the same hardware as the multiplier and divider, except for some small changes that need to be made in order to do both. But overall, all the flip-flops, which are the most cost, are saved. So the multiplier and divider has 2 separate controllers, though. They operate at different clocks because the multiplier takes 32 clock cycles to complete, while the divider takes 33. And the control signals for it is start, to let you start the counter inside the controller, a indication whether it's multiplying or dividing, and it just serially ends add or subtraction depending on the operation. On the bottom, we can see 3 different test benches for each multiplication and division, and you can take a look at that to see the results. So data hazards. So there's 3 main types of hazards. Data hazards, which are usually just dependencies on instruction, such as you're using one of the registers currently in the ALU, and the following instruction uses it as well. But without this hazard unit, it will go to the write back stage of that first instruction and will not be written in time. So the second instruction is using the wrong value. Load hazards are, it's not a register is using a value that's supposed to be loaded in by memory, but it's not there yet, similar to the previous one, just some issues with that. And then control hazards consist of branching. So when you're doing the jump, there's some issues whether you flush or not the instruction pipeline. There's various solutions. I mentioned a couple of these being the forwarding unit, hazard detection unit, and branch detection unit. And when these all come together, it's able to allow the pipeline to free up from stalls and wrong codes.
Taking a closer look, the first one we're going to take a look at is data hazards. So one way that we get by data hazards is through forwarding. So for example, if we use a register, or we write to a register in one instruction, and then on the very next instruction, we try to read from it. If we read from it, we're going to read the wrong value. So we're going to have to implement stalls. Instead of having to stall all the way through that first instruction, or well, all the way through the first instruction, preventing the second instruction from being read and executed, once we have the result in the execution stage or in the memory stage, we can forward it to somewhere else in that same instance in time, which would then allow, for example, in the middle left, the add and the subtraction then allows them to happen right after each other instead of having to stall the subtraction instruction. So for this to happen, we have to control the inputs to the ALU. So you can see the A and B are ALU inputs, and those get controlled by 3 muxes and a comparator. So if the comparator sets off or sets out a 1, then that will go to a hazard unit, which will then stall things. And I think we'll explain more about that later. But then from our forwarding unit, it controls the other 2 muxes, so mux 3 and mux 4, and make sure that the correct result gets put into the ALU at that time, because it could be reading not from the register file, but from some other point in the pipeline stage. So you can see in the bottom right, we have a basic simulation of the forwarding unit working. So load hazards, like I mentioned earlier, we have to have some sort of stall for certain instructions to be able to run one after the other. Of course, we can't always make it with forwarding alone so that every instruction can run one after the other immediately. So we implement stalls. So as you can see in the diagram on the bottom left, this will happen whenever the jump or the forwarding is too far, in which we'd have to go forward in time to receive the result for both instructions to run one after the other in the pipeline. So you can see on the bottom our simulation of just some basic code, and you can see the script as well.
Okay, so when it comes with the control hazard, we will think about the branch. So for instance, that we use the branch equal, and before that we have ALU instructions. When the ALU instructions appears before like 2 or 3 stages before the branch instruction, we don't need to stall. We just implement forwarding. But when the ALU happens before one stage before the branch, or the load instruction happens before 2 stage before the branch instruction, we need to stall 1 bubble. And for the load instruction, if it happened 1 stage before the branch instruction, we need to stall twice. So we will implement it in the hazard detection, because hazard detection is to stall based on the output of the memory, and the ALU results go back to the register file. We need to detect if it matches the decoding stage write back register. If they're equal, there will be the control hazard happen. So this is the diagram, the steps to solve this issue. First, we will place the comparator in the execution stage. Why we do this is because if we put the comparator in the decoding stage, when the prior instruction is a load or store instruction, the register file cannot be updated until it reaches the execution stage, because the forwarding happens in the execution stage. So we need to wait the data arrive in the execution stage. Then we compare if these 2 registers data are equal. Then we will put the if it's equal signal to the branch detection. In the branch detection, we will have an AND gate inside of it, and the result will be delivered by the instruction decoder with the opcode to present if it's branch equal or is branch not equal. If it's not equal, then we don't need to. If it's not equal, we need to get the complement of the if it's equal signal. So when we add these 2 signals together, we will detect if this is a branch, and we will send back to the hazard detection, and we will do the same thing as the load instruction or that load hazard or data hazard, and we will implement the stall to the pipeline register, as well as freezing the PC register write and IFID pipeline register write. And we move to the encoding part, the decoding part, and we will choose different address from the instruction register. We will have jump address, or we have branch address. So for the branch address, we will choose the sign extended immediate value and shift left by 2 or multiplied by 4 to take the offset and plus the PC plus 4, which will result the next PC value, and we send to these marks. And after that, that marks will give back the target address in the fetching stage before the PC register writes. And the PC source is controlled by the branch detection unit as well. So this is another function for the jump. The jump is similar to the branch, but it's easier, just decoding the jump instruction, and we will generate a jump signal, and we send the jump signal, if it's set to 1, it will send to the the target address as the jump address. So the jump address will first left shift. It's right here. We'll first left shift by 2, which is multiplied by 4 to be the offset. It's a relative address, and we chose the upper 4 bits PC value, and we are not going to add them, but we are going to concatenate them to generate the new jump address. And so in this part, jump is detected as the branch, but it will not. No, the jump will not be detected as the branch. It will go straight to the fetching stage to choose the PC source, but not going to freeze the PC write or the pipeline register, because jump has nothing to do with other data. It always jump to the immediate address. So we don't need to consider the header for jump. So, and we already discussed it, like the branch, how jump works. This is the last step.
So now we'll move on, just to quickly show our results for the major components. So this is the instruction test. What will handle it?
So this is based on our instruction ISA support. We have 16 different instructions, and all listed right on the left side, all the R type here and jump here. And this is the multiplier or divider testing, and this is the last one, is the branch test, control header test. And you can see on the MIPS, the value of those register will be resulted like this. And on the right side is our processes result from the Verilog test bench. And as you can see, they are matched to each other one by one for each register number that the same. And this instruction showcases the header control and as well as the all functionality of our design.
So to show the data hazards, like I mentioned earlier, there's gonna be some conflict in actually reading data from places. So for example, the first 2 add immediate instructions, one of them writes to 8, but the second add instruction will then use 8 in the next one. So it has to forward or stall. So in this case, I believe it would, I think it would do both.
It will just forward it.
Yeah. It's too much for me to think about on the top of my head. There's too many signals. Okay. But you can see the expected results are on the right from, or on the center right from the MIPS from Mars, and on the right is from our Verilog script. You can see that the registers align. So, oh, okay. The thing is blocking. I can't see which side this is. Okay. So the test calculation that you gave us was the remainder, which is, so first we do a division calculation, which is floored. That floor is taken care of by us existing in integer space and not floating point space. So it'll automatically floor for us. And then we remultiply by what we divided by, and then subtract that from our original value. So the Mars code on the left is performing that operation, and you can see our A, as it was called, is 13 in hexadecimal, which is 19 in decimal, and that's stored in T0. And then storing in T1 is what we're dividing by, which we decided was 4, which is 4 in both decimal and hexadecimal. So we should expect a value of 3. So I believe we write that into S3. So I think this was taken.
Oh, yeah, I'm sorry.
Yeah.
I think this MIPS is wrong. We didn't update it. This is our processor. It should be the correct results. So we can just look at the results.
Yeah.
Yeah.
But you can see that in S3 there is a 3 there, and we also showed you this in class. So you saw in person that it works.
Also, you can just calculate it really quick. Like 90 divided by 4 will the quotient will be 4 and the remainder will be 3. Yes.
This is me. So this is just a sample test we did where there's 2 add immediates to load values into register T0, T1, and then we're just checking branches just to see if they work. And as we can see, we're able to successfully branch to the bottom line 10. We can tell based off the result that T3 is supposed to be 49 in hexadecimal, and we look on the right side, it's 49 as well for T3. Sorry, we're using Zoom right now, so it's hard to see the thing. So this is also the other sample test. Other sample test we tried includes set less than, especially set less than being right before a branch and then a jump. This was given to us in the project demonstration, and as we can see, we gained the expected results compared to the MIPS. So for future work, we completed 3 of the stages successfully. We just have to do a quick code analysis to add to our report, and the final thing that we're looking to after the course is to actually implement it on FPGA just to gain some experience from that. And this will conclude our project. Thank you.